Well, I'm not bragging or anything. Well, when am I going to get everybody back in class? I want everybody back. One, two, three, four, five, six, 7, 8, 9, 10, 11, 12. That's half of it. Okay, what do you need to know? Nothing? You don't even know anything? Anybody start on web work? Some of the web work optimization problems are a lot messier than the ones I've been doing. I've got mine doctored up so that I can get nice, clean answers. Anybody at home need to see any web work questions worked? Nobody's answering me. We got 6 folks at home. Okay. Well, I am hoping to do these problems here. I sent to you in mail. If you didn't download them, I have 1, 2, 3 blank copies. If anybody wants one. Bigger and clearer. So remember, in these optimization problems, we're trying to keep ourselves organized as best that we can. In that, when you're doing these things, our goal down the line is to set up a calculus problem that we can find the max or the min of. Meaning, we need a function of a single variable based upon what is described in the problem. Usually the function we want is written in the last sentence. Here we wanted area. The next one, we want amount of material used. So we want a function of a single variable that does what the objective of the problem is. Getting to that function might take several steps. We'll have to do things like maybe draw a picture. In our picture, stick some variables in there for the things that we know and don't know. Then try to write a function in terms of our variables. And if our function has more than one unknown, we've got to find a number somewhere and write a side equation that allows us to substitute out the extra unknowns. Then once you have that function of a single variable, you're ready to do the calculus. The max or min occurs at a critical number. So you take the derivative, get the critical number, you make a quick check using maybe the second derivative test to see if the critical number gives you the max or the min, and then you answer the question. Easy enough? Well, let's see. We've got our first one looking at us. I don't like writing math in pen, so let me find me a pencil here. All right, a farmer has 400 feet of fencing to build a rectangular pen. So it's just like the one that we did the other day, except for we have the pen going all the way around the rectangle. Find the dimensions of the fenced plot that will maximize the area of the pen. So here we go. That's our objective. We're going to have a rectangle, and we want to maximize the area. So our objective, we want to maximize area. And since it's a rectangle, area is just the product of the 2 dimensions. Now we need to figure out what we have here. We have our rectangle going all the way around. And we've got 400 feet of fencing. So there's the number that we're going to use to get rid of one of my extra variables. So we write a side equation that gives me the amount of fencing. In this picture, have fence going all the way around. So the amount of fencing is 2 of the L's plus 2 of the W's. Now pick your favorite variable and solve for it. I can, I'll solve for L. I get 2L is 400 minus 2W. And then divide by 2. So up in our objective function, where I have the L, I'm going to put in the 200 minus W. And then I'll have my objective function strictly in terms of W. So I'll put it over here. A is equal to L times W. That's the thing we're going to take the derivative of. Let me go ahead and multiply it out. So again, if you look at the formula, I've got a minus W squared. That's a upside down parabola. So it's certainly going to have a max at the vertex. We can quickly get the vertex by finding where the derivative is 0. So A prime is going to be 200 minus 2W. Set the derivative to 0 to get 200 is equal to 2W when I move that 2W over. So W is 100. We do a quick second derivative test. The second derivative is a negative 2, so that means it's concave downward for all values of x, in particular, for all values of W, in particular for W is 100. So that says we have a max at W is 100. The question wants the dimensions, so I need both L and W. And so here's my answer back over here. The maximum area occurs when the pen has dimensions of 100 feet by, let's see where we find the other one. Over here, L is 200 minus W, so L is also going to be 100 feet. So we gotta make square. I think the one that I put on webward is that you're fencing in a rectangle and then you're subdividing it into smaller plots. So you've still got the area, but then you have more fencing to add in there. So if I made smaller plots, maybe this way, then I would just change this equation based upon how many different links I've added in. Okay. That was like your warm-up exercises. That's just like touching your toes or something. That was pretty darn easy. So let's hope that they get a little bit more challenging. Okay, the second one. A box with no top and a square base is to have a volume of 500 cubic feet. What should be the dimensions of the box if the material used is to be a minimum? It's the test. You ready for a test already? Good golly, what's today? November 3rd. We have tests way, way far away. Okay, so we want to minimize the amount of material to make an open box with a square base. So how do you figure out the amount of material? What is it that I'm going to need to know? Surface area. I'm going to minimize the surface area. So if the box is open, then the surfaces that are left are the four sides and the bottom. So our area is going to be the area of the four sides plus the area of the bottom. So let's stick some variables in there. Let's draw a picture of a box with a square base. So I'll put it over here again. Just kind of make it a bit on the tall side. And at the top, base is a square, so I'm going to use the same variable for those dimensions. And then the height can be something different. So I'll go with x's as the sizes of the base, and y is the height. And since the base is a square, all four of the lateral sides have the same area. They'll all have area of x times y. And there's four of them. So I've got area is equal to 4 times xy, and then plus the area of the bottom. That one's a square, and so that one's going to be x squared. So our objective function has too many variables. So we go back and find a number we haven't used yet, and that is this one. That's a volume. How do you find the volume of this particular box? Volume of the box, volume of the box. X squared times y. Area of the base times the height. So x squared times y. So you have x squared times y is 500. That's our side equation. It looks like it's easiest to get rid of, to write y in terms of x. So I'll divide by x squared and get y as 500 over x squared. That's going to go right here. And then I'll have my area as a function of x only. So sub it in. I'll have 4x times 500 over x squared plus x squared. We'll simplify that before we take a derivative. 4 times 500 is 2,000, and then one of the x's cancels and leaves me an x on the bottom. So let's write that first term as 2,000 divided by x. Okay. Now we've got it set up for us. The max or min occurs where the derivative is 0. So let's knock out a derivative. Can you take the derivative of 2,000 over x the way it's sitting there, or do you want me to write it as 2,000 times x to the negative 1? Had room to do it, so let's do it. And so the derivative is going to be a negative 2,000 times x to the negative 2 plus 2x. But I'm going to go ahead and simplify. Negative 2,000 times x to the negative 2 is negative 2,000 over x squared. And then the derivative of the x squared on the end gives me a 2x. Let's set that equal to 0. And so if I've got this equal to 0, I'm going to move the 2,000 over x squared over and then solve the equation in this form. I'll multiply both sides by x squared. and then divide by 2. X is a cube root of 1,000. Is that a nice number? Anybody know the cube root of 1,000? So X is 10. It's our critical number. We're going to check if it gives us the minimum. So let's do the second derivative test. Think of that as an x to the negative 2 right here. So negative 2 times 2,000 is going to give me a 4,000. Negative 2 minus 1 gives me x to the minus 3. Put it down there. The derivative of 2x is 2. When I substitute 10 in for x, the number itself doesn't matter. The sign of the number matters. So it's pretty obvious that when 10 is substituted in for x, my second derivative is positive. Second derivative is positive, means the graph is concave up. And so we have a min at x is 10. So now it's time to answer the question. We have a minimum. We want to give the dimensions of the box with the minimum material. So let's see if I can fit it over here. So the dimensions would be 10 by 10 by y, and we can get y from right here. 500 divided by 10 squared. So 500 divided by 100 will give me y is equal to 5. So the box with the minimum amount of material is 10 by 10 by 5. Is that okay with everybody? Let me get rid of that. Am I making it look too easy? Or is it just this easy for everybody? All right, well, I happen to have more, so let's do more. What is the length of the base of a rectangle with the largest area that can be inscribed in a semicircle of radius 10? Assume that the base of the rectangle lies on the diameter of the semicircle. Let me try to draw a semicircle first. That looks pretty good. And then we're going to stick a rectangle in there. And let's see, the base of the rectangle lies on the diameter of the semicircle. So maybe it does something like this. There's our rectangle. The radius is 10. And we want to maximize the area of the rectangle. All right, so the area of the rectangle is length times width again. There's too many variables. We've got to do something with that semicircle over there to figure out what to do with our variables. So let's make L the longer side and W the shorter side. Huh. What on earth are you going to do with that 10? Somehow we got to incorporate the circle of radius 10. Well, I like using coordinates. I'm going to put this on a grid. I'm going to put the origin right here. So there's the y-axis. There's the x-axis. And here's a point on the circle of radius 10. What's the equation of a circle centered at the origin of radius 10? I know? Circle centered at the origin of radius 10.
Y squared plus x squared equals 100.
X squared plus y squared is equal to 10 squared. So here's an arbitrary point on that circle, xy, where the y value corresponds to the w of the rectangle, and the x value, if this is going to be nice and symmetric, is going to be half of the L. So I know that W is the same as Y, and L is the same as 2X. Agree? So if I put that up here, I have that area is equal to 2X times Y. But here's the relationship between X and Y. X squared plus Y squared is 100. So if I take that and solve it for X or Y, I'll be able to substitute out the extra variable here. So I'm going to solve it for Y. I get Y squared will be 100 minus X squared. It's the top half of the circle, so I can take the positive square root. Y is 100 minus X squared. Now don't even think about writing that as 10 minus X. Can't take the square root of each term. That's going to go in up here where the Y is. And so my area formula looks like 2X times that Y. So I got away from the variables I started with, but I eventually got an objective function in terms of one unknown. Let's see if you can find the critical number. Take the derivative of that, set equal to 0, and solve for X. Let me know what you get. You too, playing at home, take the derivative, simplify it as much as you can so that it has positive exponents. Set it equal to 0 and solve for X and see if you get the critical number that I get. Either holler it out or type it in there when you get a critical number. Getting the square root of 50 or 5 square root of 2? Anybody in that neighborhood? Keep going. We're on the right track. You can do the product rule, right? So let me catch up with you. My derivative will be the first times the derivative of the second, which is going to be 1/2 100 minus x squared to the negative 1/2. Derivative inside is a negative 2x. And the other part of the product rule is the derivative of the first times the second. I'm going to take the term with the negative exponent and put it in the denominator. So this is going to go downstairs. I'm going to take 1/2 of the negative 2x and get a negative x. Negative x times that 2x gives me negative 2x squared on top of that radical sign. Let me go ahead and put it as a square root. It's easier to write. And then I have this one. There's a prime. When I set that equal to 0, I'm going to take the term that's negative, add it to both sides, and so that I have 2 square root of 100 minus x squared is equal to 2x squared over the square root of 100 minus x squared. Now I'm going to multiply both sides by this, so that's going to put that up here, and the radical sign will be gone. Let's see where it's going to best fit. Let's put it right here. And so I'm going to have 2 times 100 minus x squared is equal to 2x squared. Distribute the 2 to get 200 minus 2x squared is equal to 2x squared. Move the 2x squared to the other side to get 200 is equal to 4x squared. Let's get rid of the 4. 4 times 50 is 200. And now take the square root of both sides, and x is a length, so we just need the positive square root. 50 is 2 times 25, so I can write the square root of 50 as 5 square root of 2. A more cautious person than me would do the second derivative test to see if I have a max or a min there. But I don't have any room. And I feel like living a little dangerously right now. I'm going to trust that my critical point gives me, is it a largest area? So I'm not going to do the second derivative test. It looks like it's more trouble than it's worth. Second derivative is going to be big and messy. So I'm just going to assume that that gives me the max, and now I'm going to answer the question. What is the length of the base? Well, is the length of the base going to be 5 square root of 2? Now remember back up here, the length was twice x. I put this at the origin, so x only went out to here. The length of the base is going to be 10 square root of 2. And the units are going to be ambiguous. Okay, so we answer the question up over here. You guys at home, anybody able to get that critical number on your own? Good, good job. Hoorah. I don't know, I might have to turn the volume down for y'all because these guys in this classroom are really talking my head off and having a rollicking good time. We need everybody back. I need energy. I need energy. Come on. What do you say we knock out another one? Hey, where's that energy? All right, I got another one. Let's scoot this up a bit. So I gotta go that way. Let me see if I get everybody seasick. There it is. The highway department is planning to build a rectangular picnic area for motorists along the highway. It's to have 7,200 square yards. What kind of entity is measured in square yards? Area. So the area of this rectangular picnic area is 7,200 square yards. It's fenced off on the 3 sides not adjacent to the highway. What's the least amount of fencing to complete the job? So there's our objective, the least amount of fencing. We want to minimize the fencing. So let's put our highway out here. And then we've got a fence, and a fence. The fencing then is going to be this side plus that side plus that side. So let's make this a L and each of those a W. So we're going to minimize 2 times W plus L. So let's just call fencing F. 2 times W plus L. That's what we want the minimum of. Can't quite take the derivative of that yet. So we've got to go write an equation that uses our number. You said that 7,200 was an area. So on our rectangle, the area will be given by W times L. So our side equation says W times L is 7,200. So let me solve it for L. So now I'm going to take that, put it in where the L is right here, and then our fencing equation just has one variable. Here's where I let you play with it for a while. 2W plus 7,200 over W is our objective function. So take the derivative, see if you can solve for W. You get a nice whole number this time. Everybody getting W is 60? Like the nodding, I like that. So you know the steps, take the derivative. That's a W to the minus 1, so I get a negative 7,200 W to the minus 2, and I'll write the W squared on the bottom. And so we're going to set F prime to be 0. So I've got this equal to 0, means I'm going to move the 7,200 over and have it something like this. And I'll multiply both sides by W squared. Divide by 2. 2 times 36 is 72. And then we take the square root of that. Square root of 36 is 6. Square root of 100 is 10. 6 times 10 gives me the 60. I've got room to do the second derivative test. This is a W to the negative 2. So if that's a W to the negative 2 times negative 72 gives me a positive 144 over W cubed. So we put the 60 in there. Everything there is going to be positive then. F double prime is positive, which means my graph is concave up, and I have a minimum at W is 60, which is good. I wanted a minimum. But now I want to give all of the fencing. So the total amount of fencing that's this function, 2W plus L, is 2 times 60 plus L. Remember where we go to get L? Here my side equation. L is 7,200 over W, so 7,200 over 60. 6 times 12 is 72, so that should be 120. And that will be in yards. So that was kind of the opposite of what we did earlier. We had the amount of fencing, and then we wanted to maximize area. This time we've got area, and we want to minimize fencing. Just as much fun. So if you're wishing we had more, by gosh, we do, because there's a backside to this. We have done problem number 5. This is a carbon copy of the one we did before. So I'm not even going to get you started on it. I'm going to see if you can go all the way through problem 5. Make a rectangular box that's open at the top by taking a 5 by 8 inch piece of cardboard. That's kind of like a little index card. Cut out the corners and fold up the sides. Find the size of the corner square to maximize the volume of the box. This little quiz to see if you remember how we did this problem last time. Have I given you web work on this section yet? I'm not? Oh gosh. I'm gonna put harder ones than this on there. I'll open it. I'll open your web work today. Again, getting nice numbers on this one. How big of a square are you cutting out of yours? Anybody got it yet? How much?
I got the square of 1 by 1.
1 by 1? Cut out 1 inch by 1 inch, or 1 whatever, yeah, 1 inch by 1 inch? 1? So there's our goal right there, maximize the volume of a box. So if it's a box, the volume is the product of the 3 dimensions, the length, the width, and the depth. So we figure these out by starting with a 5 by 8 inch cardboard. We've got 5. That one's the 8. Move in here and cut out a square. Let's say it's X by X. That makes 4 flaps that we fold up. When those are folded up, we've got a box. So we need the length, the width, and the height of this resulting box. So this length here is the 8 inches shortened by cutting out X from both sides. So let's write that as 8 minus 2X. This width here is the 5 shortened by X on each side. So let's write that as 5 minus 2X. And then when you fold the flap up, it corresponds to the variable X itself. So we're going to have the length is 8 minus 2X, the width is 5 minus X, and the depth itself is the X. So volume is 5 minus 2X times 8 minus 2X times X. And that's the thing we need to take the derivative of. So that I don't have to do the product rule. Within the product rule, I'm going to go ahead and distribute this X, and then I'll take the derivative. So I'm going to put these two together. Write that as 8X minus 2X squared. Now I'm going to take the derivative. Here's the first times the derivative of the second plus the second times the derivative of the first. So I avoided multiplying out for as long as I could. Now I do have to multiply this out, because we need to find out where this thing is equal to 0. So let's distribute the 5 through the parentheses here. 5 times 8 is 40. 5 times the negative 4x is negative 20x. Now I'm going to distribute the negative 2x and get a negative 16x plus 8x squared. Back here, I'm going to send the -2 through here. -2 times -8x is -16x. And then -2 times a -2x squared is a plus 4x squared. The like terms give me 12x squared, -36, -46, 52x, plus 40. Does that look familiar? Did you get to that step? All right, I need to pull out the greatest common factor. I think that might be 4. Maybe. One of those 16 should be where? Uh-oh. That's going to be a 16x. And that's going to be a 16x. And there's a 20x. I think I do have all my x's. Okay. Now I'm going to look to see if I can factor this. Let's see, I'll need a 3x and an x. Factors of 10, both minus. So it's either 10 and 1 or 5 and 2. I'm thinking 10 and 1, since I knew the answer was 1. So that gives me a -10x and a -3x, so that is a -13x. So there it's factored. Now when I set each factor equal to 0, I'm going to get 2 critical numbers. There's the x is 1. This one gives me x is 10/3. But that's 3 and a third. One side is only 5 inches long to begin with. So I can't knock off 3 1/3 inches from each corner. So that one makes no physical sense. This is the only one that makes sense. Let's check to see it gives us a maximum. It's pretty quick to take a second derivative from here. V double prime is 24x minus 52. When x is 1, I have 24 minus 52, which is negative. So a negative second derivative tells me the graph is concave down, and so that is a max. You now answer the question. What size corner square? That's the x. Cut out 1 inch by 1 inch squares. Okay? Questions, anybody? Any comments or complaints? Okay, I'm going to jump over problem 6 because problem 7 is one that I'm going to put on web work. I'll put problem 6 on web work as well, but we already did that one in class last time. And I've got about, what time we get out of here, 10:50? If I got time, I'll come back to do 6, but let's make sure we can get number 7 done. Window has the shape of a rectangle surmounted by a semicircle. If the perimeter of the window is 15 feet, find the dimensions which will allow the maximum light to enter. Find the dimensions that allow the maximum amount of light to enter. Let me draw a picture and you can tell me what it is we're maximizing. Draw a rectangle with a semicircle on top of it. So how do I get the maximum amount of light in there? What am I maximizing? Overall area. We want to maximize the area. So we have 2 areas to consider, a rectangle and a semicircle. So the old rectangle has area of length times width. What's the formula for the area of a half of a circle? 1/2 pi r squared. So we've got a length times a width plus a 1/2 pi r squared. So I got an L, a W, and an R. We got to fix that. We got to work on that a bit. So let's see. Let's put the L here, the W there. So if R goes from here to here, then R looks like it's half of L. Or if you want, you can say L is 2 times R. Maybe that's better and I don't have to screw around with fractions. So we need to get the W in terms of R. We got to find a side equation. So here's a number we haven't used yet. The perimeter of the window is 15 feet. So our side equation is going to involve going from here to here to here, around the circle, and then back down. So let's write the perimeter in terms of those variables. I need to go L plus W. There's another W. What's the perimeter of half of a circle? Pi times R, because the circumference of a circle is 2 pi r, so half of a circle is just pi times r. So in our picture, we've got 2w plus L plus pi times r is 15. We said L itself was 2 times r, so I have 2w plus 2r plus pi r is 15. We're going to use that equation to substitute out the w. I can get everything written in terms of r. So let's solve for w. This says that 2w is 15 minus 2r minus pi r. So when I divide by 2, I have that w is 15 halves minus r minus pi halves r. So now I'm going to go back to my objective function and write my area strictly in terms of r. L, we said, was twice r. W is that big long line down there, 15 halves minus r minus pi halves r. And then I have plus 1/2 pi r squared. If I send that 2r through there, I'm going to get rid of all those fractions. So let's go ahead and multiply this out first. The 2 will cancel here, and I'll have 15r. In the middle, I have minus 2r squared. On the end, the halves will cancel, and I'll have a minus pi r squared. But then I have a plus 1/2 pi r squared. So if you want, you can even go further and put those 2 pi r squareds together. These two together, I have 1 pi r squared that's negative, a 1/2 pi r squared. Add them together and you get a negative 1/2 pi r squared. Whew, all that work here, and I've got my function in terms of one unknown. So from there, we're going to take a derivative and see if we can figure out what r is going to be. Are you with me to that point? So what I try to do when I'm doing these word problems is talk my way through it. Tell me what I know and don't know. See where my plan takes me from there till I can get me a function that I can take a derivative of. All right, the derivative's not hard, it's just a polynomial. So A prime is going to be 15 minus 4r minus pi r. So we'll set that equal to 0. Let's put the r's together on this side, make them all positive. So I'm going to have 4r plus pi r is 15. Let's factor out the r. 4 plus pi goes here. And so our critical number is 15 divided by 4 plus pi. A quick second derivative is just going to be negative, right? 15, the derivative here is 0. Derivative there is negative 4, negative pi. So no matter what the critical number is, I have a concave down graph, and so I have a maximum. We got to get all of the dimensions, and we've got the radius of the circle. The length and the width can be found using this step over here. So we want the dimensions of the window. We have the length is twice the radius. So if I multiply that by 2, I get a 30 on top. And that's feet. The width is this number down here, 15 halves minus r minus pi over 2 times r. And then the radius. So when was the last time you built something where the radius was something pi, has a pi in it? How do you measure that with your little tape measure? A special notch for pi? That does leave us enough time to do the one I skipped over. So if you're up for it, we got one more to go and time to do it in. Yeah. Woo. All right, back up to number 6. Cylindrical container with an open top is to hold 1 cubic foot. I'd call that a cup. I'm making a cup. There's no waste in construction. Find the dimensions that will require the least amount of material. So the amount of material, again, is going to deal with surface area. We're minimizing the area of this cylinder. Bless you. And since it's open, that area is just going to be the bottom plus the lateral portion. So here is our open top. There's the lateral portion. We know its volume is 1 cubic foot. And so now we got to figure this part out. The bottom is a circle, so we'll need its radius. Area of a circle is pi r squared. Since it's open, I just have one of those. How did we decide the area of the lateral part? What's it look like? What's the lateral portion look like if you're constructing this thing? It's just a rectangle, right? A rectangle that has a certain height. But this length around here, right, the lateral portion will look like this, where this has to go all the way around the circle. So the lateral part has area of 2 pi r times h, which gives us one variable too many. We got to get rid of either the r or the h, so we have to use the number that we haven't used yet and write the side equation. That's a volume because it's in cubic feet. How do you find the volume of a cylinder? The volume of anything is the area of the base times the height. Pi r squared times h. So I have pi r squared times h is equal to 1. Looks like that's easy to solve for h. H is 1 divided by pi r squared. So let's put that in where the h is up here. And our area function then looks like pi r squared plus 2 pi r times 1 over pi r squared. Pi's will cancel, and one of the r's will cancel. So I have area is pi r squared plus 2 divided by r. We always have to get our objective function in terms of one unknown. The rest is calculus. Take the derivative from here. 2 pi r minus 2 over r squared. Set that equal to 0. If that's equal to 0, I can move the 2r squared over. Multiply both sides by r squared. And let's divide by that 2 pi. And the 2's will cancel. So r is 1 over the cube root of pi. You could write that as the cube root of 1 over pi. But the cube root of 1 is 1. So there's our critical number. The second derivative is 2 pi plus 4 over r cubed. So even when r is a goofy number, second derivative is positive. That guarantees that I have a minimum. Second derivative is positive. So that's part of my answer. The radius of the cylindrical container has to be 1 over the cube root of pi. Now we need the other dimensions. The h is 1 over pi r squared. So h is 1 over pi r squared. R squared will give us 1 over pi square the cube root, and that'll be 2/3 power. So I can write that as 1 over pi to the 1/3, which is also 1 over cube root of pi. Can you do it? Radius is 1 over cube root of pi, height is 1 over cube root of pi. So one of the keys to doing these kind of word problems is to actually sit down and do them. Try to do them by looking at what we did in class. I'll try to give you very similar problems, but I'll try to put some in there that are different just to see if you can build your objective function from scratch. Okay, so for the most part, copy what we did in class, but then I want you to be somewhat creative on your own as well. That takes us to the end of the differential section of calculus. We're going to go and start doing integral calculus next. Suppose a physicist knows the velocity of a particle, and he wants to know where that particle is located at any time t. He should be able to work backwards from the velocity to get the position. If you know how fast something is changing, even if it doesn't measure velocity, if you know a rate of change at a particular time, you should be able to find the position at a time, or the basic setup. So we're going to do all of our steps backwards. Given that you know the derivative of a function, find the function that has that derivative. Okay? So it's going to be as easy as this. I took the derivative of something and I got 2x. What did I take the derivative of? X squared. Right? I took the derivative of an x squared. Maybe a number was added at the end because the derivative number is going to be 0. But that's what we're going to be doing. We're going to find antiderivatives. Doesn't that sound like fun? Woo! All right. Well, class be over, so I can't start it now. I got about 5 minutes, but that's enough wasting. We got the long time next time. So I'm going to put up a web work and let you guys get started on it today. And I hope I can get more people back in class. I hope you guys are doing okay at home. Ask questions if you have it. Anybody at home have any questions? Thank you. All right, feeling good, Reagan, love it. Okay, I'm gonna stop sharing. Boom, you're gone. I'm gonna end the meeting. Last chance to ask any questions before I hit the old end the meeting button.
This is one of like the only classes that I have that's still meeting in person.